Hey everyone, welcome back. In the last video, we talked about the central limit theorem, which states that as the sample size increases, typically when it's greater than 30, the distribution of the sample means approaches a normal distribution. So mathematically, the sample means follow a normal distribution with a mean of mu and a variance of sigma squared over n, where mu is the population mean and the sigma squared is the population variance. Let's revisit the red marble proportion estimation problem. So this time I increased the number of marbles from 1,000 to 5,000. Okay, and then we take a sample of 100 marbles and calculate the proportion of the red ones, which is 69%. So this 69% is our point estimate, the estimate of the proportion of the red marbles in the entire bag. Okay, so then we had two questions at the end of the video. So how confident are we in the estimation? How can we quantify our level of certainty, right? So as you can see that by just drawing 100 marbles, it's very unlikely that the proportion of the red marbles is exactly equal to the actual proportion of red marbles in the whole bag. So this is where this confidence interval comes in. Instead of saying the proportion of the red marbles is exactly 69%, we could use the confidence interval to say, I'm 95% confident that the proportion of red marbles in the bag is between 59% and 79%, which also can be written as 69% plus or minus 10%. Okay, so put it another way, if you think 69% could be off 10% from the population mean, then we can estimate the proportion with the interval 59% and 79%. The 10% is called the margin error. So our job is to determine how large the margin error is so that the interval will likely capture the true proportion of the red marbles. So how can we do it? Let's take a look at the margin error. The margin error is equal to a critical value times a standard error. Okay, let's tackle them one by one. So first, let's look at the critical value, which is also called z-score or z-value, and which indicates how many standard deviation a data point is from the mean of the data set. So to construct a 95% confidence interval, we need to find the z-score that bound the middle 95% of the area under the curve. Okay, so we actually need to find the two values of these two red dots. So how can we calculate it? So we use the Q-norm function, which returns a z-score corresponding to the cumulative probability P for a standard normal distribution. Since the area in the middle is 95%, right? And the tails on each side together so make up 5%. Because this normal distribution is symmetrical, so each tail will have half of the 5%, which is 2.5%, right? So for the upper bound, representing the top 2.5%, and we use Q-norm 0.975, which gives us 1.96. So sometimes we use 2 for convenience. With these two zero scores, we effectively capture the middle 95% of the area under the curve, giving us bounds for our 95% confidence interval. Now we're going to take a look at the standard error. Okay, if the population variance is known, then the standard error is calculated by sigma divided by square root of n, where n is the sample size. However, most of the time, the population variance is unknown. So for a large sample, we can assume that the standard deviation of the sample is reasonably close to the population standard deviation. And we can use the square root of p hat times 1 minus p hat divided by n to estimate the standard error of the population. So where p hat is the sample proportion. So we save the sample proportion to p hat, and then we calculate standard error, which is 0.046. And then we calculate the margin error. So margin error is equal to z times standard error, which gives us 0.091. And then we constructed the 95% confidence interval. The lower limit is the p hat minus margin error, and the upper limit is p hat plus the margin error, which gives us an interval from 0.599 to 0.781. So what if we want to calculate 99% confidence interval? So we just need to calculate the z-score for 99% confidence level, okay? And then it gives us an interval from 0.571 to 0.809. As you've likely observed, our confidence interval increases and our confidence level becomes wider. This makes intuitive sense because the more certain you want to be about capturing the true proportion parameter, the larger the range we must consider, right? So how the confidence interval works? Let's revisit the distribution of the sample means again. So every time you draw a sample and you calculate the sample mean, right? The mean will land close to the population mean. It could be lower, it could be higher, right? And given a sufficient large sample size, these sample means are clustered around the population mean and follow a normal distribution because of the central limit theorem, right? And based on the sample, we construct a confidence interval like we did before. But sometimes the confidence interval captures the true proportion mean. And sometimes it doesn't, right? Like the right one over here. That's why we need a confidence level. A 95% confidence level means that if we were to take the samples and construct a confidence interval from each sample, we are expecting that the intervals would capture the true proportion mean about 95% of the time, okay? So in other words, if you say that you are 95% confident, you are stating that in the long run, the intervals we construct will capture the true proportion mean about 95 out of 100 times with this method. It's important to remember that it doesn't mean that there is a 95% chance that any specific interval contains the population mean. It's about long-term frequency. And let's put this into visuals. This is what a 95% confidence interval looks like. So about 5 red intervals out of 100 didn't capture the true proportion of the red marbles. And this visualization embodies what the 95% confidence interval is about. So here are the steps to construct a confidence interval, okay? Compute the sample proportion first, and then find the critical value corresponding to that confidence level. Compute the standard error and marginal error. The last step is to construct the confidence interval. And then suppose one day your friend said half of the marbles in the bag are red. So would you take his word for it, or do you want to verify that claim? So this brings us to our next exciting topic, hypothesis testing. So stay tuned for the next video.